Welcome back to this series. In this episode, we are going to diagnose and solve the problems of this machine. And what better way to start than from the symptoms, what the machine is telling us. That is not to say that conjectures made based on symptoms should replace systematic troubleshooting. They shouldn't. But we shouldn't ignore the symptoms either, because the machine is telling us two important things with this screen. Number one, the CPU is not managing to clear screen memory. That's why we see this garble. Number two, either character generation or the shift register that spits out the individual bits of every character byte towards the screen are not working, one of the two. And that's why we only see lines and not well-formed characters on the screen. We should keep this in mind. That said, we begin just through systematic troubleshooting. What I personally like to do after I measure power levels and all that stuff, I like to look at the signals on the CPU's pins, because the CPU is a nexus of all the important signals in the machine. So I go systematically through all of them. I start from the address bus lines. You see the 0 level on my oscilloscope, and now one of the address line is showing at 1.5 volt. That's indicative that the address line is floating. And that's the same for every single address line I checked. So the CPU is not trying to drive the address bus, and it's the only thing that drives the address bus in a node system like this without DMA peripherals and all that stuff. So the CPU is not even trying to read the ROM to fetch instructions to execute. It seems to be dead. So the lines are floating, and I zoomed in into those levels, and you see that interference there. That's characteristic of a floating line. What we are picking up on that line is noise from the other lines that are switching within the CPU. So the CPU is not driving the address bus, which suggests that the CPU is sort of dead. But to confirm that, we need to look at the other signals, and that's what I'm going to do now, and I will leave you with my live narration of what I'm doing. Next one is ground. So ground is indeed at ground. So what we saw before is not a ground reference issue. Then we have refresh. Clearly it's always high or inactive, so the CPU is never refreshing the DRAM. Of course not, it cannot it cannot drive the address bus. M1, that's the instruction fetch cycle. The next one is reset is low, so the CPU is always being reset. That's a problem. The CPU is always in reset mode, and therefore the buses will float. So there are two sources of the reset signal. One of them is IC4 here, that's a 7414, which is an inverter, and output 12, if it is 0, it will become an active reset. So let's see. If we look at the schematics, the reset pin of the CPU is this here, pin 26, and reset is active low. And that's what we are seeing. We are seeing an active low level at pin 26, and that's why the CPU is constantly in reset mode and doing nothing. If we trace this line here, it goes through an inverter. IC4 here, it has, I think, 6 inverter gates. And after that inverter, it comes from this OR gate. The way this works is the following. If either this line or this line is at a logic 0, then this little circle here means that that line is inverted before the OR gate, so it will become a 1. And then if either of them is a 1, then the output will be a 1. But that 1 is inverted by this next inverter, and it becomes a 0 on the reset input of the CPU, which is active low, so the CPU is in constant reset. So you should check if either of these two lines here is constantly at 0. That would explain our problem. Now, if we trace this first line here, it goes up to another inverter of the same IC4 that has this inverter here. but this one comes from the output pin 12 of the inverter. So we should check pin 12 of IC4 to see if it is low. If it is low, it would explain the problem. We should check the same thing on pin 1 of IC31. If either one of them is low all the time, we explain the problem. If we go back to the circuit here on top, this here is just the reset timer, which makes sure that the CPU is reset when you start the computer, but then a fraction of a second afterwards it comes out of the reset state. The way it works is the following. When you start up the computer, this capacitor here, C19 22 microfarad, will be discharged. When it's discharged, there is no base potential here through this diode on the base of this transistor, the 2SC373. Therefore, the transistor is open, and therefore the 5-volt potential goes into the input of the inverter. So this will be a 1 because the inverter inverts. This becomes a 0, and the computer is in a reset state when you turn it on. But after a while, through this resistor R28, the capacitor will charge. And once it's charged, then through this diode, there will be a positive potential on the basis of this transistor. And the transistor will then close, meaning that the potential of the emitter, which is ground, will be here on the input of the inverter. And therefore, the output will be a 1, and then the computer comes out of the reset state. That's how it's supposed to work. The way this could fail is after you've charged this capacitor, if there still is no positive potential here on the base and the transistor doesn't close, then you keep putting the 5 volt on the input of the inverter, and then the output will be in ground, and the computer will be always in reset. So let's check pin 12 of IC4 first to see if we identify the problem there. Output 12 of IC4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It is low. So this is in constant reset. The input to this inverter gate is pin 13, which is ambiguous. It's just under 3 volts. It's right halfway. It's an ambiguous input, which is turning into a reset. And that comes from transistor. Comes from the collector of one of these transistors here. I have to figure out which one. The transistor in question is one of the 5 transistors that I swapped out in one of the first episodes, as part of the restoration. And when I looked at it, I realized that I installed them with the emitter and the base swapped around. I installed them wrongly, actually all 5 of them. And this explains the problem, because the base potential was going to the emitter, not to the base. So the transistor was not closing, which explains that ambiguous signal in the input of the inverter, and which in turn explains why the CPU is in constant reset. This is a wake-up call for my lack of attention. In this case, I didn't damage anything, but in another system like a 5110 or something, it could have been very costly. So I'm beating myself in the butt for this error. But let's continue. And let's swap out these transistors because I already worked that part of the board or reworked it. I'm doing the gentle approach of desoldering with desoldering wick. It's usually less stressful for the board. So I pulled them out and I installed, again, brand new ones. This time I just put a heat shrink along one pin. It's enough to prevent short circuits. You don't need to exaggerate and put little pens on all of them like I did before. And hopefully now the base potential will go into the base and the transistor will close and stop the machine from being in that reset. So let's try that out with this and turn the machine on. And look, the CPU is now indeed clearing the screen. So we have solved one problem. But we have still another obvious problem. We can see half a cursor. There are only 4 lines instead of 8. And we can't see any other character. If I type them in, nothing appears. It's like space. Except if I try some of the graphics characters. And I'll tell you the conclusion already. If the character I type in, if the first bit of every line of the character is a 1, then we will get only a full line, like there. See, only a full line. But if the first bit of a line is a 0, then we get nothing. We get an empty line. That clearly shows that it's a problem with the shift register. The shift register is not, well, shifting. It's only exposing the first bit of every line to the screen and not the next 7 bits. It's pretty certain that this is the problem. The shift register is a 74LS165 in this board. I'll show you. It's that chip over there. So we have to pull out the oscilloscope again and look at the pins on that chip, and I'm sure that that will be the problem. Okay, this may require a little more unpacking. This is a segment of the schematics of this machine. This is the LS165. That's the shift register in question, the one I showed you, IC29. The way this works is as follows. Each character on the screen is a little matrix of 8 by 8 bits. So it has 8 lines, 1, 2, and so on until line number 8. And each line has 8 bits, 1, 2, and so on until bit number 8. So there are 8 bytes per character. And the way this works is that the character generator will take each one of these 8 bytes, each one of these lines, and send it to the shift register along these 8 lines, VD0 to VD7. And these 8 bits will be loaded in parallel load, into an internal register of the shift register, which has this name for a reason. So this entire byte is loaded in one go into a register inside the shift register. And what the shift register then does, it takes the first bit of that byte, bit 1 over here, and it will send it out through this QH port. And if you follow what happens here, it has some more processing, some signal conditioning. You can ignore all that. Eventually, it makes its way to the video signal that goes to the screen. Now, after it has shown the first bit, and before the next byte comes in, what it will do is it will shift everybody one position up in this case. So what was the first bit now falls out, and what was the second bit now goes to the position of the first bit, and that then gets displayed on the screen. Next cycle, what was the third bit will make its way to this position, and then it's displayed on the screen, and so on and so forth until all 8 bits of this byte have been displayed on the screen, and that will correspond to one little line of 8 bits. Now what's happening is that this shifting is not working. If this shifting is not working, what you will have is you will parallel load that byte, and then this, what happens to be the first bit of the byte, will be shown to the screen 8 times because the other ones are not being shifted to that first position. So the other ones are just being ignored. Only the first bit is displayed, and if this bit is 1, you see a line. If this bit is 0, you see nothing. So the problem is that the shift register is not shifting the bits of the byte, and we now have to investigate why that is the case. So let's look at this shift register. The first bit is the shift load bit, so it triggers a parallel load when it's low. And you see every few cycles it triggers a parallel load. That's exactly what we would expect. The next one is the clock, and the clock, there are 2 clock inputs. One of them should trigger a shift. This one seems to be floating. Very interesting. We have a floating clock input. Let's look at the other clock input, which can also be used as a clock inhibit if it's high, and it's low, so it's not inhibiting the clock, but there is no clock coming in. That line is floating. Let's have a look at the rest. These are the parallel loads. Yeah, that looks okay. Yeah, these are the parallel bits that come in, and they all look as they should look. That's the serial and other bits of the parallel load. Yeah, the computer is loading character bytes into this shift register, but it's not shifting. Let's look at the power level. Power level is okay. It's not shifting because the clock input is floating. That explains why we only have lines, because it loads 8 bits, but then it doesn't shift, so it keeps showing only the first bit of the character line on the screen. If that bit is a 1, then you have a full line. If it's not a 1, it's a 0, then you get 8 times 0. So the problem may not even be the shift register itself, but the missing clock input, probably from the modifications. Let's have a look. Okay, let's see. The clock is supposed to come from pin 8 of IC 7, which is this one here. So this is pin 8. It should go to pin 2 of the shift register. And it doesn't go there. Interesting. The clock is also supposed to go to pin 1 of IC 9, which is this. There it goes. But it doesn't go to the shift register. It's also supposed to go to pin 9 of IC 22, which is this. So pin 9 is here. Is it 1, 2, 3, 4, 5, 6, 7, 8, 9? Also doesn't go to pin 9 of IC 22. Interesting. Another quick intermezzo to explain this. This is the oscillator, the 8 megahertz oscillator. Through a divider, this becomes the 2 megahertz. It goes this way. It becomes the 2 megahertz that feed the CPU. But in addition to that, to coming here, and it's going there, as you saw, I just checked continuity of this line, and it is going there. But it's supposed to also go to the shift register this way. This 8 megahertz signal is the one that's not getting to the shift register. And it also goes here to pin 9 of IC22. It's supposed to go there, but it's not going. And I had a quick look at the logic here. This is the stuff that eventually produces the horizontal blank. And I think the fact that this connection is broken explains why we see only 4 lines instead of 8 for the cursor character, and probably for every character. So probably the line was in fact cut here, and because it was cut here, it's not getting either to the shift register or to IC22. And this one cut here probably explains both problems. There probably are traces cut because of the modifications. And sure enough, there is the cut on the trace, exactly where I thought it would be, breaking both of the connections I talked about. There it is. It was cut by the previous owner as part of some modification. So I study the board and find a conveniently placed via already on the board. I will use that to place a bodge on the back side using very thin wire. You see me preparing that now. After I tried it once, I didn't quite like the result. So I removed everything, cleaned the solder again, and I will do it again until I am satisfied that it's up to standard. There goes the bodge again. Fairly clean, with a little hook on the wire for mechanical sturdiness. Solder it in place, and this should solve the problem. But since I have the soldering iron hot already, I decided to reflow some joints. Somebody on Twitter reminded me that the flyback usually vibrates a lot, and if the solder joints are old, they can crack. They are all working right now, but since this is a restoration, I'm going to prevent a future problem by reflowing the solder joints of the flyback, and I'm reflowing the solder joints of all the tuning potentiometers of the monitor. I forgot to do that last time, and sometimes when I tune the image, sometimes the image falls out for a fraction of a second, which is characteristic of a dry, broken solder joint. So I reflow them all, clean it all up. And once I'm satisfied with that, we can put the system back together and retest it to see if that bodge has corrected the problem. So let's have a look. Turning the system on. And monitor is warming up, and there we go. It's working now. It's working again. So yeah, that's a big thumbs up. So now, what is else left to do? We have to test the keyboard, and I go through every key to make sure that they are all working. Some of them they don't react as reliably as I wish them to react. I'm first writing hello world, of course. Then I go through the test of all the keys. The ones that don't react reliably enough, I go back with a little bit more of Deoxit D100, the one without flush action, without solvents. And I sort of squirt a little bit more. That's what you see me do now. Squirt a little bit more, press the keys again. And I did that 2 or 3 times until I was happy with it. And then the next step is to connect back the cassette player that you see there on top of a little plastic box. Everything open so I have access to the circuit in case of problems. And try to load an application. So there we are, loading an application, patience with tape loading. I do some fine-tuning of the monitor in the meantime, but it doesn't work, you see. It didn't load the tape correctly. I tried again, some more fine-tuning of the image because I'm about to put the system all back together again. That's my chance to access the trim pots inside the board. So I'm trying to load it again. Let's see if it's going to work now. Patience until it loads. That's the tape era for you there. And it doesn't work again. So I decided to adjust the azimuth screw in the cassette player. Usually you have to hook an oscilloscope to the collector of a transistor deep inside the player. You have to disassemble it again. That's the only way to do it systematically and reliably. But right now, as you would see if my big hand were not in the way, I'm just adjusting that by eye, just trying, try to load a program again. And sure enough, it loads. It does load. And there is me playing that game, but not always right. When I get killed, the screen that you see is not what it's supposed to be. And when I kill an alien, it kills me too. Every time I kill an alien, I get killed. That's not right. So the program is executing well enough for us to actually see the game, but there is something wrong. I suspect that this is a 48K program game, but remember, I reconfigured the machine for 36K, and I think that's the problem. Some of the program is not accessible because it's floating in the ether. So as it happens, I just got a new batch of 4116s, so I'm testing them all thoroughly with my tester. And if I'm satisfied they're all okay, then I start putting them back on the board after straightening the pins, as you see. And after I reconstitute that third bank of RAM, I have to readjust the jumpers to reconfigure the machine for 48K. That's what I'm doing now. And that's the result. Now all 3 banks are fully loaded with working RAM chips. Those are the jumpers there. There are 2 locations, that's CS2. Those are the correct positions for 48K. CS1 is up there on the top left. There you see it, it's in the center of the screen now. All the jumpers should be there. So now let's try and load the same game again and see if it works now. Typing load, pressing play, the usual procedure. I'm speeding it up now. And the game starts again. Let's see if I get killed if I kill them, or if the screen is incorrect after I get killed. Let's see. Still haven't killed anybody. If I were a better player, we would have resolution. There you go. I killed one of them and didn't get killed for it. Now it's working. There you go again. And when I do get killed, it's the correct screen. This one, that's the correct screen. So finally, we are through with fixing this machine. So the repair part of the restoration is done. Much of the restoration is done. What is left is to put the system entirely back together and have some fun with it. But even before I do that, I of course try a couple of other games, including Head-On that you see there. Everything is working. Everything is fine. So only one part left in this series, and that's putting the machine back together and playing some more games later on. So as I said, next time we are going to put it all back together and unveil the final result of this restoration. Till then, take care.